Hello there and welcome back to this video series on control systems. In the previous class, we have been looking at field control DC servo motor and we studied its dynamics. We derived a couple of things. We drew the block diagram, we derived the motor time constant, and we saw that armature controlled DC servo motor settles faster than the field controlled DC servo motor. What we are going to do is just build a little bit on this and try to solve maybe one elementary problem to see where all the quantities fall into place. This is the problem statement, and this data refers to a position control system. When you say position control, there is a external feedback using a potentiometer, that is the error detecting device. You have an amplifier, you have a servo motor, you have motor inertia, load inertia, motor um, viscous coefficient, and so on. We have to find what is the transfer function of the closed loop system and show the first overshoot when this system is subjected to a unit step input. This quantity first overshoot is also called peak overshoot. We'll try to solve this problem, but before that, we'll try to show all the situation in a block diagram. It's always a good idea to draw a schematic and then a block diagram. That's exactly what we are going to do. We're going to draw a schematic, and for each section of the schematic, we'll draw a block diagram. We'll start doing that, and we notice that it's a good idea to start with the error detecting device or a comparator, which in our case is a differential potentiometer. On one side of it, you have reference position. The other side has a measured position. Okay, so this is the desired, this is the measured. This differential potentiometer has a constant Kp 1 volt per radian. So it gives 1 volt output for radian, 1 radian difference between theta r minus theta o. We further go ahead by building this. We say this terminal is going somewhere and this theta O is coming from some measurement here. In a minute we will show what is that measurement, but notice that this difference between theta R and theta O is fed to an amplifier. This amplifier gives 100 milliamperes per each volt of difference between theta R and theta O. When we write the equations, I think this becomes clear. Theta r minus theta o is measured multiplied with Kp, that gives the voltage which is going to amplifier. This amplifier feeds the field and generates a field current, and you have armature with Ia constant, then you have motor inertia, and then this motor is turning with a torque Tm and angular displacement theta m. You have a viscous damping. All this motor shaft is connected to one gear with number of teeth N1, radius R1. This gear is pairing with another big gear. So this is small, this is big. So when motor turns faster, the other red gear turns slower. On this gear, we have load shaft connected, and then you have a load viscous damping, and this is fixed. So from here you measure theta O, you have reference theta, their difference is fed to potentiometer. This potentiometer generates 1 volt per radian difference between theta r and theta O. This voltage is fed to an amplifier. The amplifier generates a current which feeds the field circuit. This field circuit generates magnetic field, and when this magnetic field cuts the armature conductor, a torque is generated. When torque is generated, motor shaft turns. When motor shaft turns, this gear turns, this red gear turns, and hence theta O changes. This cycle goes on and on till equilibrium is established. Try to write equations describing different sections as shown below. We have the first thing, that is differential potentiometer. Voltage applied is constant of the potentiometer multiplied by theta R minus theta O. A block diagram is drawn. You see theta M with a positive sign, theta O with a negative sign, multiplied by Kp gives E. We draw the next section, that is amplifier. For amplifier, the current is amplifier constant multiplied by E. So this EF is obtained. Then we write the equation for the uh, next section, that is motor. Torque developed by the motor is motor constant multiplied by the current. So we have drawn this. And then for the load, we say Tm is this. We didn't consider the disturbing torque, but we can do it. It's not a big issue. But in the problem, that is not asked, and so we left it there. So this angular displacement theta m goes to a gear train, and gear train output is theta O. So you join this theta O and theta O there to form the feedback loop. Because there is a error detecting device, a sensor, this FCDC is a closed loop. Noting this, we go forward and we will identify various parameters and then do it. All that begins when you write the transfer function. This is the transfer function of the field control DC servo motor under closed loop. Inherently, it doesn't have any feedback loop. This feedback loop is what we are creating using potentiometer. Various quantities are summarized here: Jm, Jl, Fm, Fl, and you find what is the equivalent motor inertia. Note the gear reduction ratio is 1 over 5. So you do that to obtain motor inertia to be 45 milligrams meter square. 45 into 10 to the power of minus 3 kg. Similarly, you can write expressions for F equivalent. Noting J equivalent, F equivalent, you write the expression for theta O by theta R. You can do all the math, simplify and verify what is wrong. Please let me know. Theta O by theta R transfer function is obtained like this. This transfer function will compare it to the standard form, output by input, omega n square by s square plus 2 zeta omega n plus omega n square, and compare the coefficients of s square, coefficient of s, constant term. If you compare the constant term here and constant term here, here you have omega n square, here 111.11. So omega n is 10.5. And if you compare coefficient of s, 2 zeta omega n here, 0.88 here. So zeta is 0.88 by so and so, it gives to be 0.042, which is a very lightly damped system, for which percentage of overshoot. This formula we will derive later, but for now remember this to be the formula. Peak overshoot depends only on damping ratio. It is very lightly damped, so peak overshoot is very large. So we will show that on a graph here. This is the graph which shows the step response. That is, if you give a step input, the output varies something like this. In MATLAB, you can simulate it, and we are referring to this quantity as the first overshoot. It is 0.88 radians. With that, we will summarize what we have seen. A typical problem is solved to offer a flavor of the type of problems. And we note one new information we obtained is peak overshoot is 1 plus so and so quantity for a second order system. Okay, that's all we have for now. Have a great day.